Okay, so let's unshare and then Weitao, can you share? Okay. Okay. So our next speaker is Weitao Zhu from Colombia, and she'll be speaking on upper tail large deviation principle for the ASEP.
Yeah, hi everyone. So today I'll be speaking about the upper tail large deviation principle for the ASEP. The talk is based on joint work with Xiaoyang, and you can find their paper on the archive. So before I dive into the content of the talk, I'd first like to give an outline of what I'll be speaking about today. So I'll begin by introducing the model, which is the ASEP, asymmetric simple exclusion process with step initial data. And then move on to describing some of the large time behaviors of H0 of T, which is called the integrated current through zero, and is one of the important observables for ASEP. And finally, I will present our main theorem, which is the upper tail large deviation principle for the ASEP, and briefly explain how we got there. And so the ASEP is a continuous time Markov chain on particle configurations in Z. So we have x equals x1 greater than x2 and so on and so forth, where xi denotes the position of the ith particle. The dynamics of the process is as follows. For each site, I in Z is occupied by at most one particle, which has an independent exponential clock with exponential waiting time of mean 1. When the clock rings, the particle jumps to the right with probability Q or to the left with probability P. Such a jump is permitted only when the target site is unoccupied. So in order for the Markov chain to make sense, we also have to specify its initial state. And the initial configurations we're concerned with in this talk is the ASEP with step initial configuration, which means that x sub j at time 0 equals negative j for all positive integer j. So that means that all the particles at time 0 are lined up to the left of 0. And we set the parameter gamma to be 2q minus 1 and assume that q is greater than a half. So ASEP has a drift to the right. Here's a demonstration of the dynamics I was talking about. On the left, the particle cannot jump to the left because it's already occupied the site here. The site is occupied. And then on the right, it's free to jump to the left or the right. And then there's also the step initial configuration. Finally, I want to mention that when q equals to 1, the particle can only jump to the right. When q equals to 1, that's when the particles can only jump to the right. We obtain ASEP, which is totally short for totally asymmetric simple exclusion process. Okay, so we already mentioned that one of the important observables for ASEP is H0 of T, the integrated current through 0, which is defined to be the number of particles to the right of 0 at time t. For instance, in this snapshot at time t here, there are exactly 4 particles to the right of 0, so H0 of T equals 4 in this case. In fact, we can relate this global, current fluctuation phenomenon to the local fluctuations of the positions of the nth particle by observing that H sub naught of T greater than or equal to m. This event is the same as if the nth particle is at time t is to the right of 0. One of the reasons why we're interested in H0 of T is that it's the one-dimensional height function of the interfaith growth of the ASEP, which converges to the solution of the KPZ equation. So that tells us that ASEP is in the KPZ universality class. And that means that we want to understand the large time behaviors of H0 of T. In that regard, there are several results available. So first, we have the strong law, which says that H0 of T over gamma rescaled by time t converges to half, almost surely as t tends to infinity. And second, we also have the central limit theorem, which was established in the seminal paper by Tracy Woodham in 2009, that says that if we rescale or recenter this H0 of T by its mean, and then multiply it by the prefactor 2 to the 4 over 3, and rescale it by t to the third, this rescaled random variable would converge in distribution to the Tracy Woodham GUE distribution. And what's particularly interesting here is this t to the 1/3 rescaling factor, where this 1/3 is a signifier, this exponent is a signifier of the KPT universality. Another thing we want to remark here is that when Q equals to 1, that's when we're in the realm of TASEP. Equation 2 recovers the same result on TASEP, which had been established earlier in the paper by Johansen in the year 2000. Okay, so now we have the strong law and the central limit theorem. We also want to understand the tail behaviors of negative H naught of T over gamma plus T over 4. And that brings us to the large deviation regime, where the question is, what's the probability when this random variable has a deviation of order T? So here, there are actually two tails we want to consider. So the first one is the lower tail. That's when this random variable is less than negative T over 4 times Y for some Y between the range of 0 and 1. And then there's also the upper tail, which will be the protagonist of this talk. And that's when this random variable is greater than T over 4 times Y. And we predict that for these two different tails, we have two different speeds. For lower tail is T squared, and for the upper tail is T. And they also have two different rate functions. Although this hasn't been confirmed for general ASEP model, it's already been proven for TASEP, in Johansen's paper. Okay, so as the tail question, the tail large deviation principle question is not really a novel one. There is not surprising to find some previous results available in this direction already. So first we have Johansen's results where he proved both tail large deviation problems for the TASEP, and he gave his result in the variational formula. And specifically for the case of general ASEP with step initial data, a paper by Demirel, Petrov, and Sivakov from 2018 produced the following one-sided exponential bound. So for this given, bound or exponent, this function, phi plus tilde of y, which equals this value for this range of y, for a particular range, for y less than or equal to y naught, we have that the upper tail is bounded by this e to the negative t phi plus of y. And this is like a plot of phi plus tilde of y, which grows monotonically until this cutoff value y naught and stays flat afterwards. While this is a nice result, it's perhaps unsatisfying for two reasons. The first is that it's only a one-sided bound, and the second reason is that we can only, as you can see from the plot, is perhaps only possible. We can probably only extract like more useful information when y is less than or equal to y naught. So that allows us to segue into our main result for today, which is we present the first proof of the precise upper tail large deviation principle for the ASEP with step initial data. And our theorem says that for a fixed Q between a half and 1, so that's when ASEP has a drift to the right, for any y between 0 and 1, so we're no longer restrained to the range of 0 and y naught, we have that the upper tail large deviation principle has the speed t and the rate function, which is phi plus of y. And as you can probably already see that this phi plus of y is the same as a bound produced by Demirel, Petrov, and Sivakov when y is less than or equal to y naught. So our theorem actually confirmed that their bound is tight when y is less than that cutoff value y naught. Okay, so how do we do this? The idea of our proof rests upon the concept of Lyapunov exponent, which for fixed S is defined to be the limit as t tends to infinity of 1 over t log of the expectation of tau to the S h naught of t. So as you can already see from the definition, the definition encodes a lot of information about the exponential moments. Indeed, this Lyapunov exponent has a deep connection to large deviation. It is well known that using Markov inequality and tilting, we can show that the upper tail large deviation principle of log of tau to the h naught of t is the same as the Lejeune ventral dual of the Lyapunov exponent. Okay, In fact, a number of recent works on integral models have exploited this connection to find out to solve the upper tail large deviation problems. The first one in this series of recent work is by Das and Cai in 2019, where they worked on the stochastic heat equation with narrow wedge initial data and solved the KPZ upper tail large deviation problem. And not soon after, Gosho and Lin worked on the same problem, but with a stochastic heat equation with a larger set of initial data. And Lin also extended the same result to the half-line stochastic heat equation. And this approach of Lyapunov exponent is particularly pertinent for our case, for the ASEP with step initial data, because if we recall that in the paper by Demmer, Petrov, and Zibakov, where they had the exponential bound, they produced their result from performing steepest descent analysis on the exact formula in terms of probability of H0 of t, which was given in the form of Fredholm determinants from Tracy Witham's paper. During that process, when they're doing the steepest descent analysis, they had to choose an appropriate contour that passes through all of the critical points. And it is exactly this choice of contour that imposes a restriction on the range of y. And in fact, that this restriction is very difficult to prove. It's difficult to lift, if at all possible. So if we switch gears and use the Lyapunov exponent, Lyapunov moment approach, we can avoid this contour issue altogether. Okay, so that said, to exactly obtain the exponent, what we did is to combine several formulas. The first one of which is the following tau Laplace transform of H0 of t from the paper by Borodin, Corwin, and Sasimoto from 2014. And it's available thanks to the integrability of ASEP. So this tau Laplace transform is given in the form of the Fredholm determinant. And second, we also use this elementary identity from calculus, which allows us to access the n-1 plus alpha moment of a random variable u if we have some information about this expectation of f of zeta u for some function f that satisfies certain constraints. So if we let u to be tau to the H0 of t, and plug in the first equation into here, then combining both of them and using a bit of analysis, we're able to obtain control on the fractional moments of H0 of t. For instance, if we let s to be n-1 plus alpha. So here we have alpha between the range of 0 and 1. And using the continuity argument, we're able to extend this result also to integer moments. Okay, so to summarize, we proved that for a tau, or for ASEP with the drift to the right, so that's when tau equals p over q less than 1, we have this Lyapunov exponent of H0 of t, which is negative q minus p times 1 minus tau to the s over 2 over 1 plus tau to the s over 2. And using the connection between the Lyapunov exponent and upper tail large deviation principle, we're able to obtain the upper tail large deviation principle for the ASEP as a corollary. And lastly, I want to mention that we also have this following asymptotics near 0 for this wave function phi plus of y, which recovers the expected Tracy-Witham GUE upper tail decay near 0. Okay, that's the end of my talk. Thank you for your attention.
Thank you very much. And we have a minute or two. Is there any questions?
Can I ask a quick question?
Yeah.
So I was wondering if similar techniques would work to show the lower tail large deviations. So in principle, you have formulas for these exponential moments. So that should be in principle enough to control both tails, no?
Well, yeah, but so to do the tails, we need to solve the lower tail problems. We, for instance, if we can let u here to be the negative u that 1 over u that we have here, in principle it should be possible. But then we also need this function, or to this this equation here to work, but in this, but the first, the tau Laplace transform function is only for, we can only have like positive moments here. So it's, so this approach actually doesn't work for lower tail.
I see. So for the negative moments, you don't have a formula.
Yeah.
How they look like. I see. Thanks.
Other questions? Okay. All right, so we're going to take a 10-minute break. People are first welcome to stay in the Zoom. We'll continue.